Previously on The Head of a Pin.
Newton, Isaac Newton, 300 years ago, was puzzling over whether light had some sort of continuous nature or was corpuscular.
These waves that were at the basis of Maxwell's theory also had a particle manifestation.
Whenever you try to measure the speed of light, it's always the same, no matter if you're moving away from the source of the light or toward the source of the light. It doesn't matter. And that's a very weird fact about our universe. After this great revolution in the 19th century that brought together electromagnetism as a unified theory, people began to think, well, we must be able to unify electromagnetism with gravity. After all, there must be some grand unified description of the world. Well then, unfortunately, that program became more complicated when it was discovered that inside the nucleus there's this strong force holding the nucleus together. It's a completely different force. It's another force in addition to electromagnetism. It's not that far away in strength from the electromagnetic force, but it is quite a bit stronger. There's also the weak nuclear force, which is responsible for radioactive decay. And a great deal of the 20th century physics was in understanding how to describe the strong, weak, and electromagnetic forces and try to give them a unified description. We have a good mathematical framework for doing that. Gravity is left out, however. Gravity is many, many orders of magnitude weaker than these three other forces, electromagnetism and the weak and strong nuclear forces. So the hope for unifying those three is much greater than adding in gravity as well. So one good question is, why is gravity so weak compared to these other forces? Mass doesn't have this special place in the properties of bodies any longer. It's energy that has the prime thing. And we now see that mass is a form of energy. Okay? The amount of mass a body has is a measure of the energy in it, its fundamental rest energy in relativity terms. And we've learned how to take that energy and convert it into mass, or convert mass energy back into kinetic energy, the energy of motion, pretty freely.
Mass is a quantity that measures the inertia of an object, namely the resistance that it gives you when you try to push it or pull it. So a massive object, a big rock, is hard to push or pull, whereas a light object, you just can push it a little bit and it can move real fast.
So the mass is the tendency of things to stay in one place and not want to be accelerated. Right? Heavier things have less acceleration given the same force, whether that's an electromagnetic force, whether it's a push or a pull, or whether it's gravity. Doesn't make any difference. It's the tendency to something that want to stay in one place.
Some people think maybe mass isn't the most useful or the most fundamental way to describe things at all. Who knows? I think we're only beginning still in understanding the particle nature of our world. And the masses of particles certainly seem to be interesting properties, but where does mass come from is the big question confronting us right now. Why do they have mass to begin with?